Today, before I start the new chapter, let us talk about the Hess law. It'd be best if I use an example. Yeah, this is a nice example of Hess law. A minute. Okay, can you please tell me first what is an Hess law before I start?
Hess law is basically when you calculate the enthalpy of something by breaking, from my understanding, it's when you break down an equation and you find the enthalpy of specific like molecules in that are involved in the main enthalpy change to find the enthalpy change.
Uh, okay, I understood. A more refined definition, if I say so. Hess law is something like this. These are some of the essential definitions that you'll be requiring for Hess law. Like some of the terms, basically. Let's just go through once, then it will be easier for us to remember. If I talk about Hess law, so we need to know some of the essential definitions. Some of them are standard enthalpy change of formation, and then there is the standard enthalpy change of atomization. And what does the Hess law state? It states that the total enthalpy change in a chemical reaction is independent of the route by which the reactants are converted to products as long as the initial and final conditions remain the same. So they're basically trying to say that whenever we try to find so they're basically trying to say that whenever we are trying to find the enthalpy change of a chemical reaction, we don't. It's not primarily necessary to use the main route to find the enthalpy change of that specific reaction. Rather than we can use a different route like this. It's like basically vectors. Do you have maths in AS? I think you have studied maths, right? So in maths, there's this chapter called vectors, where each and every value has a magnitude as well as a direction, right? So just like that, Haskell basically states that if you want to find the enthalpy change of a specific type of chemical reaction, it's not primarily necessary to use this, the main route. We can use other routes, alternative routes, to find the enthalpy change as long as the final condition and the initial conditions remain the same. That means they're trying to say that whatever initial conditions at which we start, this is going to be equal to the final condition at which the products are produced. The conditions must not change. Like if the pressure, if you're using a pressure of 100 kilopascal, 298 Kelvin, right? Or with 1 mole DMCO, if we are using this sort of, standard temperature, pressure, or concentration, then obviously we need to ensure for the Hess law to be broken, that we need to ensure that these conditions remain the same at the end of the reaction when the products are produced. Did you get my point? This is what Hess law states. So yeah, in other words, the enthalpy change for the direct path of a chemical reaction is the same as the enthalpy change. So yeah, it's basically the same that if you find so in other words, they're trying to say that if you find the summation of these two enthalpy change right here, this also represents one enthalpy change. That also represents one enthalpy change, but we don't know what type of enthalpy change they both they both represent. It could be a lot of, it could be anything. You know some examples of enthalpy change, right? There are several types of enthalpy change. You have the change of formation, then you have the change of atomization, then you have another one which is known as the change of combustion. The fun fact is that in every case, the definition is somewhat similar. It's just that the change is here. Okay, in case of formation, 1 mole of a compound is formed from its elements in their standard states. This is very important. 1 mole of a compound is produced when we talk about enthalpy change of formation. When you talk about atomization, 1 mole of gaseous atom is produced from an element in its standard state. I mean, it's the same for both. Like the conditions for the reactants is kind of same when you are calculating for the standard enthalpy change of formation as well as the standard enthalpy change of atomization. And if I talk about standard enthalpy change of combustion, what do you mean by that? Can you please tell me?
Energy required to combust 1 mole of gaseous compound, right?
The enthalpy change when 1 mole of a reactant or a substance reacts with oxygen at its standard state under standard conditions. You get my point? So it's basically again just like the previous definitions which we have just seen. Just 1 mole of substance in this case reacts with oxygen to produce what we know. What is the end product of combustion? Carbon dioxide and water, right? So 1 mole of a substance. You have to just ensure that 1 mole of a substance reacts with oxygen. Okay, and obviously it must be at its standard state. What do we understand by standard state here? For example, hydrogen. You will never see it in solid state, right? That's not its standard state. Yeah, maybe in some cases, scientists might have, or industrialists might have, converted it. But do we find it in? I mean, normally, do you find it in hydrogen in solid? No, right? We don't find hydrogen in solid form normally, isn't it? So what will be its standard form? G. So did you understand what do we mean by standard state here?
Yeah.
Okay. Okay, so this is basically just an overview of Hess law. So if you just do an paper, I mean, just do a problem, then it'll be much more easier. Uh, okay, so let's start from the first. It will be easier for us, and we also need to know this one's enthalpy change of combustion. It will be much more easier. 1 minute. One minute. Okay, can you please find the first two, this part of the question? I think you can do it.
The change of the spirit burner is 0.57, and the change of water is 45.8.
Okay, 0.57, 0.57, and 45.8. Right. Okay. The next part is that they told you to basically calculate the change of combustion. This is pretty simple. How can you do it? Which formula do we have to do? Just try.
Q equal to MC delta T first, and then you use the enthalpy change equation, which is Q over N.
Okay, okay. Hmm. Okay, so what is the answer that you get?
For Q, I got 1400, 358.3 joules, and the
1400,
mole
300.
of
Yeah, okay, 1400,
1400, 358.
58 joule. Okay, then what
3.
did you get the enthalpy change per mole?
9.19 into 10 to the power minus 3. That's
9.1.
mold. That's moles. 9.19 is mold. And the final enthalpy change, I got mm, yeah,
Okay,
for the
first of
final
all,
one, I got minus 1562.6.
it is kind of wrong, your one. I think primarily because the moles that you got, that is wrong. Okay, first of all, let's check out. Because I
Even
just
molar mass might be wrong.
hmm. Okay. Okay, so this is the amount of mass that that reacted from the spirit burner, right? 0.57 gram. Samaya, can you hear me?
Yes, sir.
Okay, okay, very good. Okay, I'm just explaining Hess law and then we will move on to the next chapter. Please wait for a while. Okay, so 0.57 gram basically reacted from the spirit burner, right? So that will be our mass. Now, what do we know about the molar mass of 2-methyl propane 2-ol? If you just draw the it's better to basically draw the displayed formula. It's much more easier to, you know, like calculate the molar mass. I think I made a mistake. That's H. There's OH for Q. So that's our 2-methyl propane 2-ol, right? So we have four carbons, right? So 4 times 12, 5, 6, 7, 8, 9. We have 9 hydrogen, and then there's 1 oxygen, right? What do we get here? We get about 74, right?
73.
73.
Yeah, wait, let me calculate again.
1, 2, 3, 4, 5, 6, 7, 8,
73.
9. 73.
Yeah.
Okay. 2-methyl propan 2-ol. 2, 3, 6, 7, 8, 9. Okay. 48, 9, 16. 57
10,
plus 6, 67, 77.
10 hydrogen, I think. Yeah.
1 to 2 methyl propan 2-ol. 1 minute. 73, right? 73.
Yeah. No, the number of hydrogen is 10. You wrote 9.
Oh, okay, yeah. 10, 10. Sorry. I will also know.
Yes, it's 74 in the end.
Sorry. Yeah. Okay. So 74 is our molar mass. So now we know everything. We just have to plug it in. And what's the answer? Can you please tell me the mole? Mole will be, if I'm not wrong, 0.57 divided by 74. That will be, can you please tell me? It's about 0. I'm checking my calculator. It's about 0.007027 mole. That's the amount of moles that basically reacted. Okay, now we can just place it right here. 0.007027. And what will be the answer? Simra?
Yeah, I got 1864021. So
1864021. That's it.
0.053. But I mean, do you need to round it up?
4053, whatever. We can just write it in standard form in order to avoid confusion.
Mm.
You can just write 1.86. Since you gave 3 digits, so 10 to the power 6. Yeah, that should be it. That should be the answer. Joule per mole. Okay, now let's move on to the Hess law. The standard enthalpy change of combustion can be calculated using standard enthalpy change of formation. Okay, that's where Hess law comes in. State why no enthalpy change of formation value for oxygen has not been provided. Any idea why? Like, why do you think the
Form oxygen. You use oxygen to combust to methylpropane-2-ol. So since
yeah?
it's not forming anything, you can't. There's no enthalpy change of formation.
Yeah, you can say that. Mm, First things first, one thing you have to understand, there's a more refined answer to it. Uh, it's standard enthalpy change of formation. And what do we know about the definition of enthalpy change of formation? A little while ago, we have just seen when 1 mole of a compound is formed from its elements. And did you notice here one thing? Oxygen is already in its standard state. It's an element, right? So, I mean, what are you supposed to produce from oxygen? Isn't it? So that is why there is no enthalpy change of formation for this value. Did you get my point? For this for oxygen.
Yeah.
Okay. So we can just write that oxygen is in its standard state. Look, that's why I told you to check the mark scheme because you won't be able to. Okay, I'm talking to both, also Samaya as well. After you do the worksheets and after I show them in the class, obviously you're going to do the worksheets at your home as homework. After you do them, do check out the mark scheme. Okay, I think Samaya, you can see the year and the respective question numbers provided, right? I don't think it's that hard to find the mark scheme and just check it out, isn't it?
Yes.
So do check them out, and it will be much more easier for you to ensure whether your answers were correct or not. If it's not correct, then obviously you will rectify it, and even after rectification, if you don't understand, then obviously I'm there. So oxygen is in its standard state. Okay, so you might want to write this. Now the main part, complete the Hess cycle. We're supposed to find the enthalpy change of combustion of this. Sorry, did they say that? Yeah. We're told to calculate the enthalpy change of combustion of this reaction. And as you can see very clearly, this is the reaction. This is the combustion reaction. Okay, we just need to balance this reaction first. Simra, can you please try?
Yeah, I balanced it. That's the least I could do. I got 6 oxygen, 4 carbon dioxide, and 5 water.
Okay, 5 moles of water. Okay, so our balancing is complete. If I talk about the formation, what do we know about formation? That enthalpy change when 1 mole of a compound is formed from its elements in their standard states, right? So obviously, what are the elements? Let's identify the elements right now in both in the product and the reactant side. Well, we have carbon, we have hydrogen, we have oxygen. It's the same thing for in the product side as well. The only elements present is carbon, oxygen, hydrogen. That means we just have to write the elements down here. So already carbon has been written, so we can just write hydrogen, and we can give oxygen. No, not oxygen. Yeah, oxygen. Yes, yes. Did you understand? Hmm?
Yeah, understood. Don't you have to
Okay.
balance them?
Yes, sure. You have to balance them out. If you want to balance them out, if we give 5 hydrogen, then I feel like it gets balanced because we have got 10 hydrogens down here and then we have 10 hydrogens down there as well. We have to balance this. Remember, we need to balance this box in such a way so that both the reactant and the product side gets satisfied. Okay. If I talk about the oxygen part, what can we do? We can give, well, we can give, there are about 8 plus 5. Okay, before we do this, hmm, okay, there are 12 oxygen, 6 to 12, and there are 13.
I got
And
6.5 for that.
yeah, you can
Oxygen.
give you can give 6.5. 6.5 is about 13 by 2, right? 13
Yeah.
by 2, isn't it? Okay. So we can just give 6.5 oxygen. Anyways, everything is completed. We just need to now just place the values. So the enthalpy change of formation has been provided for 2-methyl propan 2-ol. You have negative 359. So that's 2-methyl propan 2-ol for 4-ol for you. So we have what? Negative 359. So if you can just write it down, negative 359 down here, because that's what basically the enthalpy change of formation represents. As you can see clearly from its standard state, 1 mole of 2-methyl propan 2 is being produced. Then the next part is we have carbon dioxide and water. Okay, now this is a little bit tricky. As you can see very clearly that 4 moles and 5 moles of water, 4 moles of carbon dioxide and 5 moles of water is produced. So whatever the enthalpy change of formation, the value is provided for 1 mole. By the way, this is only for 1 mole. So whenever you write down the main equation down here or in the S cycle, you need to multiply the given number of moles with the value of the enthalpy change when 1 mole of carbon dioxide and when 1 mole of water reacts. So in this case, obviously it's going to be 4 times negative 394, right? And since I mean the one arrow represents both the enthalpy change of formation, so we just need to summarize or add 5 times where's water? It's about 286, negative 286. Okay, so everything is complete. All we need to know is just place them in the equation. Now, if you use the vector formula or if you use the vector principles down here, if you want to find this, if you want to go from A to B, so we can go from this to this. Have you noticed one thing? The original arrow sign was upwards, but if you want to satisfy our this direction, we need to go, the in the opposite direction of this given arrow, isn't it? So what will happen? Don't you think the sign will change?
Yeah.
Yes, the sign is definitely going to change. So it's going to be plus 359. And then, hey, this one's sign is not going to change because the arrow sign is in the designated direction. So that's going to be just plus 4 times negative 394 plus 5 times negative 286. Okay. Both these, and if you just do the math, what will be the answer? You're going to get your enthalpy change of combustion. I get about negative 2647000. Oh, wait, it's in kilojoule, right? So it's negative 2647. Negative 2647 kilojoule per mole. I hope you understood Hess law. This is a nice example. You need there's another one, I guess, in the same. Yeah, I think this one. Will you
Yeah.
be able to do?
This one was harder than the one we did right now.
Sorry.
I mean, I did write down the elements. So for the box, I filled out carbon solid, half O2 gas plus CO2 gas.
Hmm. Standard enthalpy change of phosgene. Okay, we can do it. No problem. Okay. What did you write? Can you please tell me? Okay, first of all, let me read the question. Standard enthalpy change of formation for phosgene is provided. Which one is phosgene here? This one, right?
Yeah.
Okay. And what are the values that have been provided? We have been provided this one, this value right here. Okay. So this value is the value of this reaction has been provided, which is negative 107.6. So this value will be negative 107.6 kilojoule per mole, right? This has been provided. Okay. And do we think
Do we use that? Because they give us like the enthalpy change for formation of phosgene. And the Hesse cycle is for the formation.
yes, you have to give. Wait 1 minute. But before that, you need to formulate the equation. Okay, since this said to find the enthalpy change of formation of phosgene. So according to the definition, what does it mean? That 1 mole of phosgene is produced from its elements at its standard state. What are the elements in phosgene? We have carbon, oxygen, chlorine, right? So
Yeah.
carbon, solid, oxygen, gas, and chlorine. I think it's necessary to, okay, wait 1 minute. Mm,
Half oxygen.
Okay, they
Half.
told you to determine the enthalpy change of formation of for carbon monoxide, right? So the arrow sign will be upwards again in this case, isn't it? We are requiring
Yeah.
these two. These two, since we are requiring these two elements for the formation of carbon monoxide, so so our arrow sign is going to be upwards. Remember that. Okay, this is logic. Okay, so this value is provided. Like what is provided? The enthalpy change of formation for phosgene is provided. How much is it? Negative 220 negative 220.1 kilojoule per mole. So you're supposed to find X, this value right here, isn't it? Okay, it's pretty simple. Again, use the vector rule. So if you want to go, if you want to find this, so we can go this like this. Okay, so let's try. Or you can use another method. There are so many methods to be honest. Mm, okay, sorry. Okay, let's just use the main method, direction. It will be much more easier, just like the previous question. So if you want to find this value right here, I mean, if you want to find 107.6, so you just need to change this arrow sign, isn't it? So that would be negative x, then what? Negative 107.6 kilojoule per mole. Sorry, not yeah, negative. And did I make a mistake? Yeah, negative x, sorry, a little bit mistake. Negative x, and then that would be negative 220.1 is equal to negative 107.6 kilojoule per mole. Okay, now we can just take x on this side and bring this one down here. So that would be negative 220.1 plus 107.6. X is it going to be whatever the value is, which is about negative 112.5 kilojoule per mole. Do you understand?
Yeah.
Okay, so that's how you basically do Hess cycle. I think I've showed you two examples. Did you get an idea of Hess cycle so far? Simra?
Yeah. Yeah. I got it. Yeah.
Okay, fine.
Yeah.
Same,
Understood.
yeah, okay, Samya, I have a question. Did you had any question from these two chapters so far? Energetics and intermolecular forces. Sorry?
Sir, sir, किसी क्वेश्चन में प्रॉब्लम है जी
Acha,
पीछे
kun
हो
question? Which questions? Can you please tell me? Oh, which question? আমাকে বলো।
17B
Energetics. Oh, there's another Hess cycle. Simra, can you please try this? In the meantime. Hello, Simra.
Yeah. Sure.
You can take a photo, screenshot, okay? Just take a screenshot because our meeting will be over within 5 minutes. So, and this is for both of you that please try to join after 9 minutes. I will send the link. And yeah, I'm going to Samya's one. Did you take a photo? Try this by yourself.
Yeah, I have the paper with me.
Oh, okay. Just try this.
Okay.
In the meantime, 17B, you're saying. Yeah, what is the problem? Please tell me. Tell.
asking বুঝেছি but কেন হয়েছে এটা বুঝিনি
Okay, so the hydration of anhydrous copper to sulfate is reversible. So you have copper to sulfate and water. When it reacts this once, the forward reaction is exothermic. So what they're trying to say is that H forward down here is negative value. The temperature change for both the forward and reverse reactions are difficult to measure. Suggest a reason for in this case. Okay, the first reason, the temperature change to I think it must be very a piece of cake. Look, in the forward reaction, what is being produced? A solid is being produced, isn't it? Right? A solid is being produced, isn't it? It's like kind of a unit 3 question basically. So if a solid is produced, don't you think it's much more harder to calculate the temperature of a solid? I mean, specifically speaking, compared to a liquid. So we can give one example. This is a good reason we can give. Uh, or there could be another one. So yeah, solid is the best. It's the best answer, I would say. The temperature of a solid is difficult to measure. I feel like the most common sense answer. The temperature of a solid is difficult to measure because look, a solid, okay, the heat is not distributed equally in the whole structure of a solid. So it is, and when you try to heat it up, when you try to heat it up, a lot of heat gets lost to the surrounding. So it kind of becomes very difficult to measure the, temperature of a solid accurately. Did you get my point? That is why it's important. If it was liquid, it would have been much more easier because there are certain instruments in which you can use liquid, which you can use in order to calculate or measure the temperature for liquid. It's very simple. I mean, you can't you can't insert a thermometer like you can do inside a cup of liquid in there, right? You can keep a thermometer inside a cup of liquid and easily measure. But do you think it's easier to measure the temperature of a solid because you can't do it that way? So did you get my point? Overall, it's kind of difficult to measure the temperature of a solid. Okay, reverse reaction. As you can see, copper to sulfate and water is being produced. Again, you can say same thing since a solid is being present. You can write the same reason, or you can tell another one that the salt may decompose further. Well, they're trying to say is that sometimes when you try to when the whoever us or the student, whenever we try to achieve the reverse reaction, what does it mean? It's basically decomposing, isn't it? The reverse reaction is basically decomposition of hydrated copper to sulfate into its respective compounds, copper to sulfate and water, right? Now, the problem is that other than this, it further decomposes. So, if it further decomposes, when you try to measure the temperature, change, so that means those products which basically further decomposed, which got produced due to further decomposition, they will also come in our calculation or in our measurement. So that would make our whole measurement difficult to measure. Like the actual measurement will be harder. Did you get my point? So there are two ways. There are two ways you can just say. You can just say the salt may decompose further, or there is this another classic example, this one right here, which is what? The temperature is the temperature for solid is difficult to maintain. Okay, You can just write any of these two answers. I hope you got the answers. Anyways, we have less than 1 minute left. Simra, did you complete the Hess cycle? If you haven't, please try to complete before the next meeting starts. Samya, can you hear me? Samya, can you hear me? Hello, Samya, can you hear me?
Yes, sir.
Okay, we're starting kinetics and equilibrium. ঠিক আছে? I'm giving a small recap here. What is happening? Just check it out. Which conditions provide the highest yield for the forward reaction? You can very clearly see a reaction is being provided. Okay, NH4Cl and ammonia and HCl is produced. Now, what is our desired product? Our desired product is ammonia, isn't it? And the del H value is provided. Well, the del H value represents the, that the del H value basically represents the enthalpy change for what? Forward or backward? Forward reaction, right? I'm talking to Samya.
Yes, sir.
Yes. Okay, the forward reaction has a positive value, positive enthalpy change value. What does it represent? Is it endothermic or exothermic? It's endothermic, right?
Thermic.
Yes. Now, the question is, if we increase the temperature, we know that the temperature, we know what? We know that the equilibrium is going to shift towards the endothermic direction. That's what the that's what our Le-Chatelier's principle says. According to Le-Chatelier's principle, what does it states about the Le-Chatelier's principle? That if we increase the temperature in a reversible reaction system, the position of the equilibrium is going to be shifted towards the endothermic direction. In this case, the forward reaction is endothermic, right? So we will be requiring to increase the temperature, because that's how we'll be able to we'll be able to increase our yield, as the forward reaction is endothermic. So C and D is out of the equation. This leaves us A and B. Now, among A and B, we need to determine which, high or low pressure. Now, again, according to Le-Chatelier's principle, that if we increase the pressure, the position of the equilibrium tends to shift in that direction where there are fewer moles. Again, we can see in the reactant side there are 1 mole, and in the product side there are 2 mole. So if there is high pressure, if we increase the pressure, equilibrium will shift in the backward direction. So that's again contradicting our goal in order to achieve the highest yield, which is getting higher amount of ammonia, but we are not getting it here. So obviously A is also out of the equation, which leaves us B as our sole answer. Did you understand, Samya?
Yes, sir. Thank you.
Moving on. Anyone? Simra, Samya, try. Can you tell me what is the answer? I think I've explained it a little bit. Use the pressure knowledge. It's all about pressure here. Simra, can you try? Look, one way, to identify in which way the equilibrium position basically, changes is by checking out the color of the respective reactant in the product. Okay, so as you can see very clearly, the mixture is pale brown at the initially. So what does it state? It basically states that the mixture consists of relatively higher amount of NO2 compared to N2O4. Did you get my point? Why is it pale? Because there are some N2O4. That is the reason why the brown has become a little bit of pale. Now, when the mixture is compressed, what do we mean by compressed? Do we increase the pressure or decrease the pressure? We increase the pressure. Exactly. So if we increase the pressure, what do you think is going to happen here? Look, it's going to be a little bit
It's
tricky,
gonna
but
shift to the right side, so there's gonna be more N2O4.
okay.
So it's gonna get lighter.
Yeah, it is going to get lighter, but there is a trickiness down here. So you're trying to say that if we increase the pressure, it's going to shift in the right side, right? But remember one thing, the thing about gas is that when you increase the gas pressure, when you basically compress the mixture at first, some of the N2O4 goes in the left side, I mean, the equilibrium tends to shift on the left side. Like you have to compress what you need to compress any one of the gas, right? So we can clearly see that the reactant is NO2 here. So if we compress the whole system by increasing the pressure of NO2, then what is going to happen? At first, the equilibrium is going to turn darker, and then at one point, in order to achieve the stability, it will move in the designated direction, which you said fewer moles if we increase the pressure. So since
Can
we
you repeat
increase,
the part? Can you repeat
sorry,
the part how it gets darker? Because I didn't get that.
I'm saying that since we need to increase we need to increase the reactants, what's it called, pressure, in order to compress the whole system, right? So if we increase the reactants pressure, so at first it's going to turn darker, right? And then it's going to turn lighter because we are increasing the pressure of this NO2 here. Did you get my point? And why it becomes lighter at the end? Because the equilibrium at the end shifts in the right side, because we know that according to Le Chatelier's principle, if you increase the pressure, the equilibrium tends to shift in that side where there are fewer moles. So you can see there is one mole and that's 2 mole. Okay, so it's going to be darker first, and then it's going to become lighter, not lighter. Did you get my point? This is much more detailed way to answer this question. That's why I told you it's a little bit tricky. Did you get my point?
Yeah.
Okay, very good. Okay, this is a very nice question. Both of you try to jot down the points in 2 or 3 minutes. Just jot down the points. What are the reasons why you know a low initial yield is acceptable in the industrial process? Read the question and try to solve, or just tell me the points. No need to write the answer. Okay, could you guys do it, or just tell me the points? Simra, try at least.
So so the question was to explain the chemical reasons for the conditions used. So I explained the chemical reasons first. So I said the pressure is comparatively lower than a lot of other industrial reactions. It's a fixed atmospheric pressure. So that means the pressure is sorry, it's higher. The pressure is relatively higher. So since it's higher, the equilibrium is going to shift to the right hand side where there are fewer moles of gas. Therefore, there's going to be a higher yield of ethanol. And then that's my first point. And then I was like 300 degrees Celsius is also like a very high temperature to use.
Okay.
Is that right? 'Cause I feel like it doesn't go because we are trying to achieve the yield of ethanol. So.
Okay. Fine. Uh, let's try to understand the question. Ethanol can be made in industry by the reaction of ethene with steam, okay, using phosphorus 5 acid catalyst. Our first point here is also important, which is here we are using a catalyst. Gone. Second point that we need to check out is we need to check out the endothermicity, the exothermicity of the forward reaction, which is negative 45 kilojoule per mole. The reaction is carried out at 300 degrees Celsius in 60 atm, and initial yield of 5% is achieved when the ethene and steam first passes through the reactor. Now they told you explain the reasons for the conditions used. Like, why do you think these conditions, 300 degrees Celsius and 60 atm, and catalyst was used? And why such a low initial yield? Why do you think 5% is acceptable in the industrial process? Why? You just have to do it. আচ্ছা, মানে প্রথমত হচ্ছে there are two ways you can do this. Like, first of all, if we increase the temperature, if temperature is increased, do you know the Maxwell-Boltzmann curve, Simra?
Yeah. Yeah.
Okay, if temperature is increased, what happens? Can you please tell me? More number of particles gain activation, gain energy greater than the activation energy, right? So if temperature is increased, more number of particles gain energy greater than the activation energy, and so the rate of reaction increases. Okay, fine. Well, that's a good thing for the industrial process. You're increasing the rate of reaction. But there is a catch. What is the catch? Look, it's exothermicity, right? So if we increase the reaction, the equilibrium is going to shift in the endothermic direction, which is the backward. Yeah, exactly. So, but high temperature, we can say, reduces the yield. And my point. So that's the temperature factor gone. Okay. Secondly, why we are using a catalyst here? Well, what is the job of a catalyst? It's pretty simple, right?
Increase the rate of reaction.
A catalyst increases
That's requires the activation energy.
by decreasing the activation energy using an alternative route. I mean, that's how catalysts work. For example, if I draw a reaction profile down here, you must have seen this. This is our delage, and that is our reaction profile, right? So that's EA for you. That's the uncatalyzed. Uncatalyzed. If it's catalyzed using catalyst, then did you see there's a drastic change in the activation energy with catalyst? Did you get my point?
Yeah.
Using it, so that's the alternative, basically. Using an alternative route. So that's gone. So now the question is temperature. So we need to go to a compromise, right? So the problem with temperature is that if we increase also there is problem, but if we increase also there is benefit. So we need to get into a compromise. So the compromise is that high temperature of 300 degrees Celsius is used as a compromise. Hence, high temperature of 300 degrees Celsius acts as a compromise between rate and yield. Okay, if you increase the pressure, what happens? The pressure is another factor here. What happens? Does the yield increases? I think the yield increases because if we increase the pressure, what happens?
Yeah.
There are fewer moles in the product side, so
Yeah.
obviously equilibrium shift in the right side. Pressure of the system is increased to the right side. There are fewer moles and this increases the yield, obviously. Okay. So some of the points that I have discussed, did you understand why temperature compromise is used? Like why do we have to compromise to a certain temperature? I think you understood that. Why did we use catalyst? And about the pressure case, we also discussed. And last thing that you need to just give a conclusion is that they say low initial yield is acceptable in the industrial process. See, first things first. The unconverted reactants, like they said what 5% is achieved, right? So can't we use the unconverted reactants for recycling? I mean, look, these type of questions you need to find the positive, the positivity in every point. That's it, nothing else. So look, I found the positivity in this negative line, that even though 5% initial yield is produced, what's the positive side? The positive side is that we can use the unconverted reactants to be recycled again. Do you get my point? Like not all are getting what's it called, reacted to produce what's it called, ethanol, right? For example, what about the other 95%? Can't we use them again for recycling, right? I mean, we can again react them together to produce ethanol, isn't it? So that's what you're going to write, that even though a low yield we can use the unconverted reactants again for, did you understand, Simra?
Yeah.
Look, in order to write these 6 mark questions, there are many ways. You need to talk about the factors which are affecting the equilibrium system. What are the factors? Well, you have got temperature, you have got pressure, you have got the endothermicity or the exothermicity. These are the 3 factors, as well as catalyst, if there is any. Obviously, there is catalyst here, so you're going to talk about catalyst. So that basically sums up your 5 to 4 marks. The 5th mark, you're going to give a conclusion that why such a low initial yield, except you need to find the positiveness from this statement. What is the positiveness? Okay, fine. Low initial is acceptable. What is the compromise here? I mean, in other words, what is the compromise here? That okay, fine. I accepted 5% yield is enough for me. So what is the compromise here? Why did I accept it? Because I am thinking in another sense that I have got a huge amount of unreactant reactants present, which I can recycle back. So that is kind of decreasing my cost, isn't it? Did you get my
Yeah.
point? For recycle,
Yeah.
which greatly
For the
decreases.
catalyst,
Yeah, sorry, please tell.
for the catalyst part, can we also say that they use a catalyst so that um or they use a catalyst because when you use a catalyst, you don't have to use as much of a high temperature. So to prevent yield from
First,
decreasing
I
further.
think I think we have talked about the activation energy. So that basically sums up the low temperature. Like
Okay.
decreasing the activation energy literally means using a lower temperature and using an alternative route. Look, decreasing the temperature or whatever. This was basically IGCSE level or IGCSE definition. Basically, when you're trying to whenever you try to write about catalyst at the AS level, always try to write what I just wrote down here. Decreasing the activation energy using an alternative route, because that's how it makes more sense if you check out the reaction profile. Do you understand?
Yeah.
Okay, it's more professional basically. Have you written the 6 mark question down? No, right? Or you can take a picture if you want. Both of you, Samya and yeah, what's it called? Simra. Take a picture and write it down.
And
Uh,
how long are you gonna take the class for? Because I have to go to school in like 20 minutes.
no problem. I will just leave after a few minutes. Most probably 5 or 10 minutes. 5 minutes, no problem. Okay, fine. I think we're done. Okay. Did you take a picture? Both of you?
Yeah.
Samya.
Yes, sir.
Okay, the product, okay, let me finish this and then I may make you leave. The product of the reaction is a product of ethanol and water. Explain why ethanol and water mix together fully. Okay, that's a very nice question, and to be honest, it's the easiest. Uh, First of all, whenever we want something to mix with water, we require a bond to be produced. What is that specific bond? Can you please tell me? Anyone?
Hydrogen bond.
Exactly,
Hydrogen.
hydrogen bond. So we can write when they mix together, they can form hydrogen bonds with each other. Okay, why they can okay, no need to talk about why. I mean, you can just draw the diagram also and you can just show it that way. Okay, can you tell me why? How do you think it's possible to produce hydrogen bond between them?
Ethanol is an alcohol, so it has OH minus. It has the OH group, and water obviously H2O. So the um yeah, they form hydrogen bonds to
Okay,
like
check this out.
yeah.
Check out this diagram. This is our favorite ethanol down here, and then we have water. We know that ethanol, water, like partially positively charged oxygen atom, and then we have the partially negatively charged oxygen atom down here. So for the production of an hydrogen bond, what do we require? Well, we require hydrogen's presence. Well, here you go. You have an hydrogen's presence from our ethanol side, and from the water side, we'll be requiring an element which is much more electronegative than hydrogen. So in this case, oxygen is present. So since the two conditions are met, remember every time two conditions must always be met for the production of hydrogen between any two reactant or molecule. Get my point? What are the two conditions? The first condition is that hydrogen must be present in any one of them. And secondly, a higher electronegative element than hydrogen must be present in the other element. Otherwise, if these two conditions are not fulfilled, then hydrogen bond won't be produced. So in this case, it is being, so this will be our hydrogen bond. Did you get my point? And what
Yeah.
is the angle? Bond angle is 180 degrees. Hydrogen bond. Eta ki? How much is this much? 104.5, right?
Yeah.
Sorry, by the way, do you understand Bangla?
I do, but it's not like
Hmm.
that level. But it's okay. Like I can understand a few.
Okay, no problem. So if you just draw this diagram, you can easily get 2 marks. If you want, you can get easily 2 marks if you just draw this diagram. Otherwise, you just have to write it professionally using Word.
Don't you have to explain why they say fully?
Yeah, there is it. When they mix together, they can form hydrogen bonds with each other. Now the rest part, like the next thing that you have to write is what? That এই যে আমি যেটা বলছি, that hydrogen has to be present, then what? Oxygen and everything, what I just told, the two conditions, and it is present, so hydrogen bond is present. Rather than writing, you can easily just draw it very nicely and easily get the 2 marks. Okay, it's much more easier to
Mm.
draw, isn't it? Rather than writing. So that's why I said. Okay, Samya, did you understand?
Yes, sir.
Okay, Next, if we move on to ethanol, ethanol can be oxidized using a solution of acidified potassium dichromate seeds. Well, this is our favorite oxidizing agent you will find in the AS level anywhere, basically. Failing solution, I mean, in organic chemistry, we will check it out more broadly. Ethanoic acid and another organic acid are both possible products. Acha, if we oxidize, ethanoic acid and another product is produced. Can anybody tell me what is the another product? That is basically structure Y. Do you guys know? I don't think you know, right? Uh, uh, since both of you did organic chemistry, look, primary alcohol. Ethanoic acid is what? Okay.
Carboxylic.
Yeah. When primary alcohol is oxidized, always try to remember this chart. It's very important. When primary alcohol is oxidized, then we tend to produce aldehyde. Then we have, if we further oxidize aldehyde, we get carboxylic acid. Okay. And if you reduce carboxylic acid, we get aldehyde. And if you reduce aldehyde again, we get primary alcohol. Primary alcohol, you know what? First degree alcohol, right? I think you understand what's primary alcohol. So how do we basically oxidize? Well, we can use K2CR2O7, the oxidizing agent. We can use Fehling, or we can use Tollens. Okay, same thing goes here as well. Same thing, like uh, K2CR2O7, Fehling, Tollens. There is another oxidizing reagent which you can easily use in order to convert primary alcohol directly to carboxylic acid without getting aldehyde, and that is that is very strong. It's much more stronger than these three, which is KMNO4, potassium manganate 7. These are some facts you should remember, basically. Uh, are you right, guys? You can take a picture if you are not writing. Simra, are you seeing?
Yeah.
Okay. And secondary alcohol, you have ketone. You cannot further oxidize ketone because it's just not oxidizable. You can reduce, though. If you reduce carboxylic acid, you get aldehyde. And what is the reducing agent? LiAlL4. What is the name of this? I think you guys know this. What is the name? Anyone? You know? Lithium tetrahydroaluminate. It's a reducing agent. Again, you can use LiAlH4 in order to get primary alcohol if you reduce aldehyde. In this case, also same K2CH2O7, failing, and in this case LiAlH4. You cannot further oxidize ketone. Okay. Okay. Please take a picture of this one, or have you written it down? Both of you. Simra.
Yes, taking a picture.
Okay. So please write it down. So you can guess what is the other structure. It's an aldehyde, right? So since it's ethanol, then obviously what will be produced? Two carbon aldehyde will be produced. Like the aldehyde is going to contain two carbon, and we know the aldehyde's functional group is CHO. So this is going to be our other structure. So you have ethanol, basically oxidized, being produced ethanoic acid and aldehyde. What is this called? This is
No,
acid. Sorry.
no, it's not. That's an acid, right? Ethanoic.
No, no. 1 minute. 1 minute. Oh, sorry, I made a mistake. Yeah, not mistake. Sorry, it's correct. So what do you call this? Ethanol. Okay, so this is the structure basically. State the conditions needed to maximize the yield of each product. Okay, how can you maximize the yield of this product? Any idea? How can you do it? Simra, can you try? I'll tell, no problem.
Could you show the question again?
Like how can you the products that are being produced is ethanoic acid and what? Ethanol, the aldehyde. How can you maximize
Yeah.
the yield? Okay, first of all, in when we try to basically find when we try to basically collect ethanoic acid, which process do we use? Heat under
Oxidize. Okay.
reflux. Do you know what's heat under reflux?
No.
Oh, you did not learn unit 3. In unit 3, basically, uh, so this is the round bottom. This is the pear-shaped flask, and here you have a Bunsen burner, which is basically heating up the ethanoic acid. So what happens is that not all of the ethanoic acid, evaporates. Some of the ethanoic acid evaporates, and then evaporates, and then here the fun fact is that some of them basically. Sorry, I forgot. There is a condenser here. 1 minute. There is a condenser here. Have you seen a condenser at least?
Yeah.
Yeah. So what is the job of the condenser? It is to basically cool down the environment, right? Water in, water out. So the fun fact is that when you heat it up, ethanoic acid evaporates. Not all evaporates. Let's say 50%. So when they come back, what happens is that some of them, like what happens is that some of them, the basically again condense back and comes to the reaction mixture. Here, remember one thing: we have the reaction mixture. I mean, if you do the reaction mixture, what are we doing here? We're basically doing the oxidation process here. Ethanol plus oxygen, right? I mean, the whole mixture is down here, and we're heating it up. The benefit here is that all the ethanoic acid will react eventually, because do you think the ethanoic acid is going out? No, some is getting evaporated and then coming back and then condensing back and coming back again, so that it can react with the unreacted oxygen. Do you get my point? Like this basically ensures that all the ethanol basically sorry, not ethanoic acid, I forgot, ethanol. This ensures that all the ethanol basically reacts with the oxidizing agent. Did you get my point?
Yeah, I got it.
So that is what heat under reflux is. And for Y, which is what? Ethanol, well, you can use any of you just have to basically mention any one of the physical process that you have learned in unit 3. Simple distillation, right? Since it's an liquid. Aldehyde is a liquid, by the way. It's not
Yeah.
gas. Remember that. Okay, that's it. Up to this much. And I'm going to send the PDF. You're going to both of you, the homework is to do from number 4. Okay. And with this, our chapter will be completed. And of course, before in the next class, we'll try to solve your doubts if you face any from this worksheet, okay, or from this chapter. Then we'll move on to the next chapter, which is tomorrow. So your homework submission is to ensure that you